In the beginning, there was the Big Bang. Well, perhaps stretch is more appropriate. There almost certainly wasn't a bang at the beginning of the universe, nor did the universe expand into anything. Rather, it spread or stretched out, all at once, extremely quickly. We do not know much about the start of our universe, but we do know that it was hot. Very hot. Temperatures exceeding 10 to the 32 Kelvin. Dense, too. All the matter in the universe in a space smaller than the nucleus of an atom. Our story starts at 10 to the minus 35 seconds. The universe has undergone massive expansion known as cosmic inflation. From the size of a subatomic particle to the size of a football in a blink of an eye. A football of pure energy. Governing this ball of energy is just one ultimate force. A superforce, in which all the fundamental forces are combined. In this state, the universe is so hot that matter and energy aren't just equivalent, but exactly the same. The ultimate force begins to split into its four unique parts as we know them today. First to split is gravity, perhaps surprisingly the weakest of the four. Next, the strong nuclear force, followed by the weak and electromagnetic forces. At 10 to the minus 32 seconds, the mass particle, the Higgs boson, appears, and with it pairs of quarks. Emerging from gluons, the quarks pop in and out of existence for the tiniest glimpses of time, annihilating each other as they do so. From here, a battle emerges between matter and antimatter. The statistics favour matter. For each million quark pairs, there is one matter quark. Matter prevails, and all the significant antimatter is annihilated from the universe. We don't know why this anomaly occurred, but this imperfection led to the universe as we know it today. The time is now 10 to the minus 9 seconds. The universe is 1 billion kilometres in diameter. That's still only just over the distance between the Sun and Jupiter. This relatively small universe has cooled to a point where the quark pair production cycle has stopped. The few quarks left over from the annihilation start forming new particles. Hadrons, which include protons, neutrons, and other less stable particles. Leptons, like neutrinos and electrons, also begin to appear. A whole second has passed. The universe, now 100 billion kilometres across, is cold enough for neutrons to decay into hydrogen atoms. Neutrinos decouple and begin travelling freely through space, creating the cosmic neutrino background. It's similar to the cosmic microwave background, we'll come on to that later, though helpfully completely undetectable. This relatively cold universe is still 10 billion degrees Kelvin. 4 seconds has now passed. The universe is now too cool for hadron-antihadron and lepton-antilepton pairs to be formed. A similar process to the quark annihilation takes place for hadrons and leptons. Protons, neutrons, and electrons annihilate with their antimatter counterparts. Our new environment is a hot, ionic, opaque soup of atomic nuclei and electrons. The photons, though many, are unable to freely roam the universe. Instead, they can only interact with matter. We'll now jump to 380,000 years after the beginning of everything, and the universe is 3000 Kelvin. It's now cold enough for free electrons to attach themselves to protons in a process known as recombination. The cooler temperatures cause photons to decouple from matter. The photons move about freely in the now transparent universe. This is the origin of the cosmic microwave background. The then homogeneous temperature has since redshifted into the microwaves we detect today. Along with the Hubble's constant, it remains the strongest evidence for the Big Bang. 150 million years pass in what is called the Dark Age, a period of universal darkness. Even though photons now travel freely, there are still no stars or other light sources to brighten up the night. Gravity, long in the waiting, makes its first starring appearance. In the 150 million years that have passed, despite the still expanding universe, the particles have been collapsing into huge clouds and nebulae. These nebulae grow bigger, denser, and hotter. So hot and dense, the particles fuse together, emitting huge amounts of energy. Nuclear fusion. The first stars are born, and light fills the universe for the first time, 400 million years after the Big Bang. These first stars are huge and hot, hundreds of times bigger than our Sun. Their lifetimes are short and end in massive supernovae, an explosion which expels debris, new heavy atoms. Out of the ashes rise more stars, colder, smaller and longer living. The new stars cluster, and 700 million years after the Big Bang, galaxies form. One of them is our own, the Milky Way. We skip forward to 8 billion years after the Big Bang. Stars have born and died, solar systems created and destroyed. In one corner of the Milky Way, a new star is forming, our Sun. Around it, debris collects, the foundations of our planet, the Earth. Wait another 2 billion years, the conditions are finally right, and life in the form of bacteria emerges. Another 3 billion years, multicellular life. For 100 million years, the earliest of animals. A meagre 225 million years, the extinction of dinosaurs. And wait a teeny 65 million years, and hey presto, Homo sapiens have evolved. Civilizations and empires have risen and fallen, cities built, wars fought. This brings us to today. We've briefly been through the history of our entire universe and the history of the Big Bang. But what's next for our universe? The future of our universe is complicated. Our current observations have shown that the universe is in fact accelerating in its expansion. This is not expected, because with all the mass in the universe, we expect it to be slowing down. It would be like throwing a ball in the air and watching it fly faster and faster. So scientists need an explanation for this. They came up with the idea of dark energy, a kind of outward pressure, pushing everything in the universe apart. Although we know it must exist, nothing is known about the nature of dark energy. How dark energy works and how prevalent it is in our universe will affect our future. Currently, there are 3 possible scenarios: the Big Freeze, the Big Rip, or the Big Crunch. The Big Freeze, or heat death, is the most likely scenario for the end of our universe. Over the next few trillion years, the universe continues to expand. As things fly apart, the universe cools down, star production grinds to a halt, and galaxies die out. Eventually, over an incredibly long time, every atom in the universe decays into photons, and all that remains are black holes. These also eventually disappear, radiating away through Hawking radiation. This is the end. Nothing changes anymore. The universe is dead. The second possible scenario is dependent on dark energy becoming stronger over time. Called the Big Rip, everything flies apart, much like in the heat and death scenario, as dark energy increases. Eventually, particles and even atoms are torn apart on a fundamental level. These are humbling possibilities, leaving the universe dead forever. The final scenario, called the Big Crunch, has more attractive prospects. In this case, dark energy's effects are beaten by gravity. After trillions of years, the universe contracts in a reverse Big Bang. The galaxies fly towards each other, and everything collapses to the centre of the universe. As things come together, the temperature increases to extreme proportions, similar to those we had at the Big Bang. Eventually, everything compacts, and black holes swallow up all the matter. Every black hole then combines into a supermassive black hole which devours everything in the universe, including itself. This could be followed by a new Big Bang, and a new universe in a big bounce. The theory suggests that this has happened many times before and will continue, going through a cycle of expanding and contracting indefinitely. We've looked at the beginning of our universe and the formation of the world as we know it. Only time will tell what the future holds, but one thing's for sure: this universe will not last forever.